Hi, and welcome to this new video on interpreting Microsoft's Phi-3 model with a method called LogitLens. This video will hopefully be one of a few different videos I want to make around explainability/interpretability of deep neural networks. So specifically discussing different methodologies that we can use to understand how did a deep neural network reach the decision that it did. This video will be around LogitLens, which I think is a very nice and very simple methodology to decode intermediate representations, aka all the outputs from the different hidden layers, in order to understand what do they actually represent. So first, a little bit about the Phi-3 model that I will be using. It's going to be this Phi-3 Mini with a 4K context length, and it has additionally been instruction fine-tuned, both supervised fine-tuning and direct preference optimization. In terms of the architecture of Phi-3, it starts with this embedding layer, which projects us from our vocabulary space, which is in this case 32,064, to our hidden dimension 3072. Then there is a bunch of different layers which consist of input normalization, multi-headed attention, two MLP layers, one that projects from this 3072 upwards, and another one that then projects from this bigger space back down to this 3072. And then there are residual connections both from the attention and from the MLP. And the thing to stress here is that the output from each of these layers basically has the same dimensionality, which is the batch size times the sequence length times this hidden dimension 3072. And then finally, we have this output projection layer, which is a linear layer which projects us back from our hidden dimension into our vocabulary size dimension, so that our final dimension that we get from the model output is this batch size times sequence length times the size of our vocabulary. So then, what is this LogitLens methodology that I want to talk about? Where I first found it is on this Less Wrong blog post by Nostalgia Prize in August 2020. And it was introduced for the GPT model, which basically has a very similar structure to what we just said for the Phi-3 model. There's this projection layer that goes from vocab space into hidden dimension space, in their case 16,000. Then there are all these different layers that modify this 1600 dimensional vector many different times, same as in our case with all these different attention layers. And then there's a final layer which projects us back from this hidden dimension into our vocab space. And then what the paper or the blog notes is that basically we thus have this kind of dictionary or matrix W that allows us to move between vocab space and embedding space, or embedding space back to vocab space. And specifically, if we think about what are these vectors in embedding space representing, at least for two of them, for the very first one and for the last one we know. For the first one, we know that these are the embedding vectors from the input tokens. And for the last one, we know that they represent the output logits when projected back into our vocabulary space. And so the observation is, okay, why don't we apply this matrix W, this kind of like decoder layer that we use at the very end, to also decode all the layers in the middle? May we get something sensible out of those decodings? And the answer is yes. This is one of the results that they show on the blog post. So here they start with this prompt, specifically we train GPT-3, for which the output tokens are as I show here. And then basically what we can do by using this decoding with this LogitLens, this projection matrix W from all the intermediate layers, we can understand what is kind of happening to our token, our input token, as we move through the layers. So specifically, let's look at the word specifically. We see that it starts out with chinny in the very first layer, so it's already quite far from our meaning of specifically, interestingly. Then it goes into target focused, updated, targeted, which kind of remains close-ish in semantic space, I guess, to specifically, until finally in layer 32 it becomes we, and then finally a comma, which is the correct next token prediction. And also here in color they show the logit value of each of the tokens, aka kind of like the confidence that the model has in this particular prediction. Now, how can we apply this LogitLens methodology for Phi-3? It's very, very simple. The output, as I already said, from each of the Phi-3 layers that we have is of batch size times sequence length times this hidden size 3072. We have this final layer that allows us to move between embedding size and output size, aka vocabulary. And what we then basically do is we just take the matrix from this final layer and we use it to decode each of the outputs from all of our hidden layers. Since they're all the same size, we can easily apply this matrix. Okay, so let's see how we can actually code up this LogitLens methodology and also apply it to a very simple example on Phi-3 to understand how is this example being processed by our model. So here I have already loaded my libraries, and then I'm also going to load my model. Let's wait for the checkpoints to load. And then here we see this model architecture that we already saw before, consisting of the embedding layer, the 32 different multi-headed attention layers, and then the final embedding that we will use to decode the outputs. Then let us define also a particular input text, which will be very simple in this case. It will have this structure of 1 is followed by sunshine, 2 is followed by apple, 3 is followed by koala, 2 is followed by apple, 1 is followed by sunshine, blah blah. So then basically whenever I input this 1 into the model, I want it to output obviously sunshine. So I want it to have understood this particular structure that I have. So let's first test whether this actually happens. So for this, I'll do the following. I will first tokenize the text. Then I will generate, in this case, 3 new tokens using model.generate with the input being this text tokenized. And then I will decode back the output in order to understand the decodings. And let's see what happens if we are running this. So we see that the model indeed has correctly outputted sunshine to follow my number 1, which is good. Now will come the main part, which is actually the defining of the LogitLens methodology. So let's start with that. So we will call the function decode token with LogitLens. Very original naming. We will input the model, we will input the device, we will input the tokenizer, the particular input text, and then also I will have this tokens to gen, which by default I will set to none. And what this tokens to gen will mean that in case I also want to decode some new generated tokens, so understand how their representation was changing, I can also use I can also first generate a few tokens and then decode their hidden states. So let's see, we will first start with embedding the inputs and then running this tokens to gen, so running this generation where I will generate whatever is the specified number of tokens to gen. Let's copy this from my example. So here what I do is I just take my input text, I tokenize it, and then what I do is I run the model.generate in order to generate tokens to gen number of new tokens. These I then add to the text, my original input, and then I have this new input, which will be the thing that I'll then be decoding later on. Here I also compute text tokens because it will be convenient for us to also know the complete tokenized input. Alright, then what do we need in order to actually apply this LogitLens methodology? We need the output from this linear layer that allows us to project from hidden state size to the vocabulary size. So let's get that. So let's get the decoder head. We can call it classifier head is model dot, in this case I think it's called LM head, and this should basically be a linear layer which maps this 372 to our vocabulary space, which is not 5000 as my Copilot says, but it will be 32064 if I remember right. And then what we will do is we will get the hidden state. So basically, whenever I run this inputs, which in this case, either if I don't have any tokens to generate, will just be my tokenized input text, or it will be my tokenized text where I have in addition also generated a bunch of new tokens. So I will run this through the model, and I will get the hidden states from each of the layers that I will want to decode. So I will say hidden states is model inputs, comma, output hidden states is true dot hidden states. And then I will essentially need to run a loop over all these hidden states and then apply this decoder head, this classifier head, to all of these hidden states in order to get both my decoded tokens as well as my logits, because I might also want to look at the numbers in my predictions. So for this, let me just copy it over again from my example, and then I will walk through it. So this will be the code. Essentially, what we have done is we have gotten these hidden states. I will create two dictionaries, one decoded intermediate token and one decoded intermediate logit, which, by the way, in my case will not be the logit because I'll actually pass them already through a softmax, but okay. I will then loop over all the layers in my hidden states. And I will apply my classifier head, so this decoding mapping, to each of them in order to basically map my hidden state, which is of size batch size by sequence length by 3072, back to something of dimensionality vocab size. I will then also get the probabilities, so I will pass these decoded values, aka my outputs from my classifier head, through a softmax, because again, in this case, I wanted to get probabilities and not the logits. I will take the maximum element, where I take the maximum over the last dimension, basically selecting the token in my vocabulary space with the highest softmax probability. And then I decode this token. I also compute the logit, and then both of them, I add them to my dictionary so that my final output will basically be this. I will return these text tokens, so these tokenized inputs that I'm using. I will return the decoded tokens and the decoded logits. Okay, so let's run this guy. And then basically let's test this methodology on this example that I had before. So basically this text of like this sunshine koala things. So in order to do that, let's say the dict output will be the output from this methodology, where we pass in the model, the device, the tokenizer, and the text as the input. And I'll keep the tokens to generate to 3, so that we basically generate 3 new tokens after the prompt that I gave into the model. Then we can say, okay, the decoded tokens will be dict output decoded tokens, the decoded logit, same thing, and then I'll also just get these text tokens in order to also analyze those. So here we can run this part, which should be pretty quick. Let's first do a very simple thing where we just print out all the decoded tokens from each of the layers. So basically, let's just iterate over the length of these decoded tokens, like this. And then we will say, okay, print decoded tokens elements, like so. And let's see if this works. It does. Okay, so here basically what we already get is in each of these lines, I plot or I print the decoded tokens from the first layer, second layer, blah, blah. And what do we see here? Is there anything already noteworthy? Some Russian, I guess, in between, which is interesting. There's some ban, apple, which makes sense. Then there's some sunlight, light. Okay, interesting. Let's also plot this in a way similar to this original blog post. Let me again just copy this in and then I'll explain what I'm actually doing. So I will choose a number of tokens that I actually want to visualize. And the way I want to visualize this is that basically I will want to show for each of the input tokens that I had, how their representation changes as I progress through the layers. And in addition, I also want to add the color that represents the probability. So here I define the set of tokens that I want to visualize, in this case token 35 to 42. I get the tokens I want to visualize and the logits I want to visualize, which are not the logits but the probabilities. And then I essentially generate here this image that will show us these different decodings with also the probabilities. So let's run this and then hopefully we will see something a little bit more structured. Okay, so what have we got here? The 35th token is the comma, 36 is nothing, then there's like the one double dot sunshine. So specifically everything following, let's say 1, so token 37, 38, 39, let's look a little bit into how the model goes about generating from one double dot this sunshine representation. So initially the 1 starts with, at some points again, ST, and then it goes into the double dot, which makes sense. The double dot itself, screen, ADR, and sun. Okay, so it already starts to more or less represent something close to what it should be representing at the 22nd layer already. The sun itself token first starts off with NY, which doesn't make much sense. Then already light, which makes sense, like kind of semantically light, sunshine, they are similar. And light, light, light stays around in this layer 16 to 22 until finally layer 23-ish, we actually get SH. And then SH itself, first not very sensible things, until eventually only at the 25th layer it becomes light, which is not actually correct. And then it goes into settings for some reason until finally it converges to ein. So anyways, the thing that I like about this method is that it kind of allows you to see how is the model getting the decision that it is getting. Sometimes it starts off with some completely incorrect, or at least not necessarily sensible to my interpretation tokens, and then usually already around the middle layers it starts to converge to something that is more or less semantically similar to the final token, and sometimes even already directly the final token. Alright, so basically I showed you how we can use this LogitLens methodology, very simply extracting this last layer mapping from hidden size to vocabulary size in order to decode also intermediate representations. I showed it on a super simple example with this sunshine and koalas, where I wanted to see how is the number 1 transformed through the layers to sunshine. There are actually a lot more cool applications also using LogitLens, and there's specifically one I want to mention, which is this paper called Do Llamas Work in English? On the latent language of multilingual transformers. So from the abstract of this paper, what they say is we ask whether multilingual language models trained on unbalanced English-dominated corpora use English as somehow an internal pivot language, aka whether whenever you give them a particular prompt to process, which might not be in English, whether the model first in its intermediate representations translates it back to English before actually then moving on to the original language that it should be answering in. And I think this is funny because if you think about when you're learning a new language, or when I'm learning a new language, initially you first really start to translate every word back into the language that you're most familiar with, like your operating language, until it becomes more natural to maybe also think in that language, the one that you were learning. So let's quickly look at one of the results from this paper. So what they do here is they show the model tokens from a translation prompt where they say français fleur, And then in Chinese, they want the model to translate flower into Chinese. And then if we actually look at these final couple of tokens, how the model changes their representation in order to finally perform the translation into Chinese, what you see is that around like this 21, 23, 19-ish layer, the double dot gets transformed at some point into the flower, and also the very last space also has at some point a flower representation before actually transitioning into the correct Chinese translation of flower. And this is interesting because it somehow shows us indeed that the model does some internal mappings maybe back into English as its operating language before only in the final layers, and unlike we saw before maybe already in the middle layers making the correct token prediction, here really only in the final layers does it actually go back to the correct target language that we had. So yeah, that's it for this video.